If you wear glasses, you know that amazing moment, right? When the world just snaps into focus? Well, behind that little bit of magic is some seriously cool science. And today, we're going to demystify it all and figure out what those numbers on your prescription really mean.
You know that little card you get from the optometrist? It's covered in all these numbers and signs. Kind of looks like a secret code. Well, guess what? By the end of this, you're going to know how to crack that code. We're going to take the journey from blur to absolute brilliance.
Okay, so let's just dive right in. Before we can really get the solution, we gotta understand the problem. Why do some of us even need glasses in the first place? Well, it all boils down to one fundamental idea in optics.
And that idea has a fancy name, ametropia. Sounds complicated, I know, but all it means is that your eye isn't bending or, refracting light perfectly onto your retina. Think of the retina as the movie screen at the back of your eye. If the focus is off, the picture you see is blurry. Simple as that.
So, if ametropia is the general issue, how do we figure out the specific kind of blur you've got? That's what your eye exam is for. It's all about pinpointing exactly how your eye is missing that perfect focus, which leads us to some really common errors.
What's so cool here is how simple it is when you break it down. If you've got myopia, you're nearsighted. That just means your eye has a little too much focusing power, and the light comes to a point in front of the retina. With hypermetropia, or farsightedness, it's the exact opposite. Not quite enough power, so the light tries to focus behind the retina.
And the fix? It's just so logical. To correct myopia, where the eye is too strong, we use a minus lens to take away some of that power. And for hypermetropia, where it's too weak, we use a plus lens to give it the boost it needs. It's all about getting that focus point to land perfectly on the retina.
But what happens if the problem isn't just about being in front of or behind the retina? Well, that's where astigmatism comes in. With astigmatism, your eye isn't shaped like a perfect sphere. Think basketball. It's a little more like a football. This shape makes light focus in two different spots, which causes blur pretty much everywhere. It needs a special kind of correction.
Which brings us right back to that secret code. We now have all the pieces of the puzzle we need to finally understand what's actually written on your prescription. So let's break it down number by number.
So, check out this sample prescription. That first number, the +2, is the sphere. That's the part that corrects your general farsightedness or nearsightedness. The second number, +1, that's the cylinder, and that's the power needed to fix the astigmatism. And that last number, 90, that's the axis, and it tells the lab exactly where to put the cylinder correction.
Now, this is super important. That axis number isn't about power at all. It's about direction. Just imagine a little protractor laid right over your eye. That 90 we just saw means the cylinder power needs to be oriented vertically to cancel out that unique, football-like shape of the eye.
And here's a little inside scoop for you. The very same prescription can be written in two different ways, either with a plus cylinder or a minus cylinder. Opticians use this quick three-step formula called transposition to flip between them. It's the exact same correction, just written in a slightly different optical language. Okay, so we've officially cracked the code on the prescription. But how do we go from a bunch of numbers on paper to a real physical lens you can see through? Well, that's the next step in our journey, actually making the thing.
You know, lenses have come a long, long way. The first ones were just flat pieces of glass. But if you've ever looked through the side of a cheap magnifying glass, you know how distorted everything gets? Modern lenses are bent, what they call a meniscus shape. This brilliant design gives you way clearer vision when you look away from the center.
So how in the world do you put an astigmatism correction on a curved lens? You can't just use a simple cylinder anymore. The solution is something called a toric surface. It's this incredibly complex shape, kind of like a slice from the side of a donut, that has two different curves ground into one surface. This is what lets us have both the astigmatism correction and that modern bent lens design. But just getting the shape right is only half the battle. You see, every lens surface naturally reflects some light, which creates annoying glare and makes things less clear. That's where anti-reflection coatings come in. These are super thin layers that are engineered to let the maximum amount of light pass right through the lens and into your eye. And this number really shows you why that coating matters so much. A modern high-index lens, the kind they use to make strong prescriptions thinner, can reflect a whopping 14.1% of the light that hits it if it doesn't have an AR coating. That is a huge amount of lost information, and you really notice it with things like oncoming headlights when you're driving at night. So, the lens has been prescribed. It's been designed with all the right curves, and it's been coated. We're done, right? Not quite. There is one last, absolutely critical step that makes sure all this amazing science actually works for your face. It's called the vertex distance. It sounds super technical, I know, but it's really simple. It's just the measurement of how far the glasses sit from your eyes. And getting this distance right is non-negotiable if you want the lens to work the way it was designed to. This quote explains the physics behind it perfectly. Your prescription is calculated to work at a very specific distance. If you change that distance, even a little bit, you actually change the power of the lens. Moving a plus lens away from your eye makes it feel stronger. Moving a minus lens away makes it feel weaker.
And that is why your optician is so careful about how your frames fit your face. Especially if you have a stronger prescription. A shift of just a few millimeters is enough to make the whole thing feel, well, wrong. That final fitting is what truly customizes all of this science directly to you.
So there you have it. From ametropia all the way to vertex distance, we've gone from a simple blur to the incredible, intricate science of clear vision. You've cracked the code on the prescription, you've seen how the lens is made, so the next time you put on your glasses, you'll really understand the brilliance behind what you're seeing. And it makes you wonder, right? Now that you can see this clearly, what other complex things in your world are just waiting to be explained?